Chapter the DNF block elements. After studying this unit, you will be able to learn the positions of the DNF block elements in the periodic table, know the electronic configuration of the transition D block and the inner transition F block elements, appreciate the relative stability of the various oxidation states in terms of electrode potential values, describe the preparation properties, structures and uses of some important compounds K2Cr2O7 and GaN-4. Understand the general characteristics of the D and F block elements and the general horizontal and group trends in them. Describe the properties of the F block elements and give a comparative account of the lanthanoids and actinoids with respect to their electronic configuration, oxidation states and chemical behavior. Now, iron, copper, silver and gold among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as Thorium, palladium and uranium are the providing excellent sources of nuclear energy in modern times. The D block of the periodic table contains the elements of groups 3 to 12 in which the D orbitals are progressively filled in each of the 4 long periods. The block consists of elements in which 4f and f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The name transition metals and inner transition metals are often used to refer to the elements of D and F block elements respectively. There are mainly 4 series of the transition series: 3D series cadmium to zirconium, 4D series yttrium to cadmium, 5D series lanthanum to hafnium to mercury, and 6D series which have actinoid and elements from hafnium to Cn. The 2 series of the inner transition metals, 4F cerium to lutetium and 5F thorium to lawrencium, are known as the lanthanoids and actinoids respectively. Originally, the name transition metals are derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Originally, the name transition metals are derived from the fact that the chemical properties are transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium and mercury of group 12 have full D12 configuration in the ground state as well as in their common oxidation state, hence they are not regarded as transition metals. However, being the end members of 3D, 4D and 5D transition respectively, their chemistry is studied along with the chemistry of the transition metals. The presence of partly filled D or F orbitals in their atoms make transition elements different from that of the non-transition elements, and transition elements and their compounds are studied separately. However, the usual theory of valence as applicable to the non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold and platinum and industrially imported metals like iron, copper, titanium belong to the transition metal series. In this unit, we shall first deal with the electronic configuration, occurrence and general characteristics of the transition elements with a special emphasis on the trends and the properties of the first row 3 transition metals along with the preparation and the properties of some important compounds. This will be followed by the consideration of certain general aspects such as electronic configuration, oxidation states and chemical reactivity of the inner transition metals. Transition element D block. Position in the periodic table. The D block occupies a large middle section of the periodic table, flanked between S and P block elements of the periodic table. The D orbitals of the penultimate energy levels of the atoms receive electrons, giving rise to 4 rows of the transition metals such as 3D, 4D, 5D, 6D. All these series of the transition elements are shown in table 4.1. Electronic configuration of the D block elements. In general, the electronic configuration of the outer orbitals of the elements is n-1 D 1 to 10 and S1 to 10 except for palladium where its electronic configuration is 4D10 5S0. N-1 stands for the inner d orbital, which may have 1 to 10 electrons, and outermost ns orbital may have 1 to 2 electrons. However, this generalization has several exceptions because of very little energy difference between n-1d and ns orbital. Furthermore, half and full completely filled set of orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configuration of chromium copper in the 3D series. For example, consider the case of chromium, which has 3d5 4s1 configuration instead of 3d4 4s2. The energy gap between the two sets 3d and 4s of the orbitals is small enough to prevent electron entering into 3d orbit. Similarly, in case of copper, the electronic configuration 3d10 4s1 and not 3d9 4s2. The ground electronic configuration of the outer electron orbits of transition elements are given in table 4.1. The electronic configurations of outer orbitals zinc, cadmium, mercury are represented by general formula n-1 d10 ns2. The orbitals in these elements are completely filled in the ground state as well as in the common oxidation states. However, they are not regarded as the transition elements. The d orbitals of the transition elements protrude to the periphery of an atom more than the other orbitals S and P. Hence, they are more influenced by the surroundings as well as affect the atoms or molecules surrounding them. In some respects, ions of a given dn configuration is equal to 1 to 9 have similar magnetic and electronic properties. With partly filled d orbitals, these elements exhibit certain characteristic properties such as display of various variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic properties and magnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in the properties of the transition elements of the horizontal row in contrast to the non-transition elements. However, some group similarities also exist. We first study the general characteristics and their trends in the horizontal rows, particularly 3D, and then consider some group similarities. One question, example 4.1. On what ground can you say that scandium Z is equal to 21 is a transition element but zinc Z is equal to 30 is not? On the basis of incompletely filled 3D orbitals, in case of scandium atom in its ground state 3D1, it is regarded as a transition element. On the other hand, zinc atom has completely filled d orbitals in its ground state as well as in its oxidized state. Hence, it is not regarded as a transition element.